Okay, so let us continue the discussion on axial flow compressor. So, now we have come across different efficiencies and the difference between different efficiencies. So, this is where we looked at that the relationship between adiabatic efficiency and the polytropic efficiency. So, and we said that for low pressure ratio, that means the when the pressure rise is low, this adiabatic, polytropic and stage efficiency, they are quite approximately same. Now, we can now look at the relation between stage efficiency and entropy. So, we can so the entropy diagram, the TS diagram that we have already drawn, we can refer to that, and what we can write that ds is Cp T naught minus R dP naught by P naught. So, it corresponds to same pressure curve. So, ds is Cp d T naught by T naught. So, which means the delta S is Cp ln T naught 3 by T naught 3 S. So, one can write T naught 3 by T naught 3 S is e to the power delta S by Cp. Similarly, T naught 3 by T naught 1 is T naught 3 by T naught 1, T naught 3 S by T naught 3 S, which is T naught 3. So, that is just a simple algebra that one can use, and you get T naught 3 S by T naught 1 e to the power delta S by Cp. So, stage efficiency would be H naught 3 S minus H naught 1 by H naught 3 minus H naught 1, which is T naught 3 by T naught 1 into e to the power minus delta S Cp minus 1 divided by T naught 3 by T naught 1 minus 1. So, further simplification, or rather alternatively one can write that stage efficiency is P naught 3 divided by P naught 1 gamma minus 1 by gamma by P naught 3 e to the power minus 1. So, what it happens that the losses in compressor blades rho may be radially related to entropy generation by the adiabatic form, which is ds minus R dP naught by P naught. So, that is what it does. Now, we can similarly, like centrifugal compressor, we can actually look at the characteristics performance of multi-stage axial compressor. So, this is performance. So, what we have to do as like we have to identify the variables. So, we are interested to know PRC, eta C of a compressor, where PRC is the pressure rise, and so my P naught 2 and eta C, this would be function of mass flow rate, P naught 1, T naught 1, rotational speed, gamma r, nu, d and other design. So, these are the complete specification of the geometric shape of a machine, where 01 is inlet, 02 is outlet, okay, and nu is kinematic viscosity, d is the characteristic size or length, typically this is the tip diameter of the first stage rotor. So, we got the total number of variables here are 9, and we have mass, length, time and temperature. These are the primary, these are the independent variables. So, we have non-dimensional groups of 9 minus 4, which is 5. Now, gamma and design are dimensionless. So, we need 3 more dimensional groups. So, m dot, which would be m dot gamma r T naught 1 divided by P naught 1 d square, and nu corresponds to Reynolds number u d by nu, which is omega d d by nu d square by nu. So, work would d by gamma r T naught. So, that means P naught 2 by P naught 1 and eta c, they are function of m dot gamma r T naught 1 by P naught 1 d square omega d gamma r T naught 1 omega d square by nu and design. Now, for a given machine, design is fixed, okay, and nu is also almost constant for a particular working fluid over the temperature range. So, that reduces this P naught 2 and eta c to be function of 3 different gamma r T naught 1, P naught 1 d square d by gamma r T naught 1 omega d square by nu. So, typically the compressor operates at very high Reynolds number. So, at that range performance is almost independent of Reynolds number. So, once we say that, so at high RE the performance becomes independent of RE. So, this guy drops out and we end up with the group which is function of gamma r T naught 1, P naught 1 d square and omega d gamma r T naught 1. Since for a given compressor, D is fixed, R is fixed for air. So, we can drop them from this non-dimensional group, and what we can retain or rather we have is function of m dot by root T 1 P naught 1 and n by root over T 1. So, we can further modify the choice by m dot T naught 1 by P naught 1, which would be m dot root theta by delta, and this T naught 1 would be n by root theta. So, where we define theta is T naught 1 by T naught 1 of a standard day, and delta P naught 1 by P naught ratio of P naught 1 of a standard day, where typically the T naught 1 standard day would be 288.15 Kelvin and P naught 1 standard day would be 101.325 kPa. So, these choices now brings back to these two non-dimensional group. Now, can take care of the variation and the ambient conditions also compared to the standard atmosphere. Now, once we plot these curves, let us say P naught 2 by P naught 1, which one can also write eta stage u delta V theta by R T naught 1, and here m theta by delta, this is what we get, and this line is the, so this is the variation of, so these are 0.7, 0.8, roughly 1. So, this is my surge line, and when I look at eta c versus m dot delta, so they are like this. So, this is 0.7, 0.8, 1. So, that is also variation with this. So, performance characteristics of an axial flow compressor is same as the centrifugal compressor. So, they also suffers from stall, surge, choking. So, in compressor choking, flow does not necessarily reach to the sonic velocity. So, keep that in mind. This is different condition compared to compressible flow when we talk about the typical convergent divergence nozzle, where the flow choking means it reaches the sonic condition, but in compressor that does not necessarily mean it reaches sonic velocity. As we have talked earlier, the possibility of flow separation is higher at later stages. Now, flow separation may reduce the effective flow passage such that the latter passage work as throttling valve, and also in the surge its violent unstable condition or rather operation of the compressor at low mass flow rate. So, one can think about this is unsteadiness, it is unstable operation of compressor at low mass flow rates. Okay. So, the best operating point is very close to the surge point. Now, as a designer, one has to prevent the surge and also extend the some limit by shifting the surge line to the left. That means, this line it should be shifted more towards the left, so that we have a better operational line. As in case of centrifugal compressor, rotating stall or stall is also present in axial flow compressor. So, you have stall, you have rotating stall. So, those things what we have already discussed while talking about the centrifugal compressor, they also do present in axial flow machine. Okay. So, obviously, this possible flow separation occurs at the high or very low angle of attacks. Now, there could be boundary layer limitation. So, when boundary layer separates, it causes the compressor to stall. So, separation can cause fall in pressure rise and efficiency. So, there would be fall in pressure rise and efficiency. So, boundary layer separation can occur at end walls or at the blade surface. The blade surface can be passages can be considered to be diffuser, air has to move against a negative pressure gradient. So, boundary layer separation can occur. Since Cp is delta P by half rho W I square. Now, when Cp greater than Cpc, which is the critical one, so boundary layer separation takes place. Okay. Typical value of Cpc is 0.4 and this. So, now one can think about how this can be prevented. This can be prevented by proper blade design and also add or some suction in blades. Now, there could be another factor which is the compressibility effect. This is also possibly compressibility effects. So, this could be there. So, once we have high speed flows which could be detrimental to the blade, transonic and supersonic flows induce shock. So, shock on blades, this will have excessive lead to excessive performance loss and shock induced flow separation. So, when there would be high speed flows like transonic and high speed or supersonic flows, there could be oblique that could have shock induced on the blades, which may lead to the shock induced separation or something like that. So, these effects are more severe at front stages. So, this kind of issues which would be the shock induced separation or blade stresses and loading on blade would be more severe at the front stages. In later stages, what happens, the temperature goes up and velocity goes down, which means the Mach number also goes down and compressibility effects become insignificant. So, obviously, there is always a limit to the speed of an aircraft due to compressibility effect. So, use of diffuser blade in front of the compressor reduces some of the compressibility. So, use of diffusers blade in front of the compressor reduces compressibility losses. So, these are the different factors or effects that one can think about considering them in the system. Now, little bit more on to the design aspect. So, if we look at some of the basic design parameters, we have now the pressure ratio per stage is expressed as pi s 1 plus eta s t lambda u v z by C p t naught 1 tan beta 1 minus, so tan beta 2 gamma by gamma. So, this is sorry, this would be degrees of reaction, not lambda, degrees of reaction. So, to obtain high pressure ratio per stage, it is needed to have. So, if you want high pressure ratio, number 1, high blade speed, that is u, second, high axial velocity, that is v z, third, high fluid deflection, that is beta 1 minus beta 2 in rotor blade, fourth, high stage efficiency. So, these are some of the requirement, but one can see when you increase the rotational speed, which is obviously there is a limit to that what one can do, because there is a structural load or the stresses would increase on the rotor hub. So, further increase in the rotational or the axial velocities, that means u and v z is also limited by the tip Mach number. So, compressor in the old ages had a maximum tip Mach number around typically less than 0.0, which has nearly been doubled for the present transonic compressor. So, in the old days, this Mach number, tip Mach number used to be 0.8, now it is 1.4 to 1.7. Also, this fluid deflection angle has upper limit, which is determined by the diffusion factor, and stage efficiency has several loss limitations. Now, just to look at this kind of things, when we talk about high blade speed or axial velocity, we have different loads. Some of them, like one is the centrifugal stress. So, what happens? So, let us say if we have a rotor blade like this, and so let us say surface so this is plan from area, DFC, this is hub, this is tip, hub. Now, this is DR, this is R, this is RT. Okay. So, centrifugal stress depend on the rotational speed omega, blade materials rho b, and height of the blade Okay, so the maximum centrifugal stress occurs in the root. So, now as we can see, so the centrifugal force which arises from this particular element. So, that element, if we look at it, dFc is omega square r dm, okay, or rather delta m, where omega is the rotational speed, r is the radius of the blade element and having a mass of delta m. Now, if it is a length is dr, then my delta m is rho b a dr. Then the maximum centrifugal stress at the rotor is summation of the centrifugal forces of all the elements of the blade from the hub to tip. So, that can be divided by the cross sectional area. So, one can write max is omega square by a root R h to R t R del m, or similarly rho b omega square a root R hub to R t R a delta r. Now, you can have some special case, you can consider some special cases. For example, let us say the blade has constant area A is constant, and then at blade height the maximum stress would be sigma max is rho b by 2 pi n square R t square minus R h square, which is 2 pi n square rho b a. So, if a is pi R t square minus R h square, which is the annulus area, then my tip speed is omega r t, which is 2 pi n r t, then sigma c max is rho b u t square by 2 1 minus square, or I can write sigma c max is rho b u t square by 2 1 minus xi square, where xi is defined the root to hub tip ratio. Now, the other case could be for linear variation of the cross section area with radius, where sigma c t max could be rho b u t square by 2 1 minus xi square k, where k is a factor 1 minus d 2 minus xi square divided by 3 into 1 minus xi square. So, d is the tip to root area ratio, and typical values of k goes between 0.55 to 0.65 for tapered blades. And other case could be area, or the area is inversely proportional to the radius. So, this would be constant by r, or inversely proportional to the thing, since r a r equals to r t a t. So, r a would be k, then my sigma c max would be rho b square by a r r hub r a dr, which is rho b omega square k by a r to r hub dr. So, this would be rho b u square xi minus xi square. So, the same equation can be applied for both fan and compressor. For fan, the blade height is for fan the blade height is long, so which develops large tip rotational speed, and the hub to tip ratio is small, thus the tensile stresses are expected at blade root. So, the same thing one can apply to both compressor and the fan. So, now the other parameter that one can look at is the tip Mach number. this is also quite important, because the most of the axial flow compressors are operated at transonic range, where there could be tendency of shock. So, the maximum Mach number in the axial flow compressor occurs at the blade tip. So, we should look at this parameter also in details, what could be the blade tip Mach number and all this. So, we will just stop here and continue this discussion of the blade tip Mach number and other factors in the next section.